Hey everyone, welcome to my stream. Just want to hear the song a little bit. It's kind of awesome. In case you're wondering, it is, let's see here. This is OC Remix, which basically streams music from, basically remixes of video game songs. And the one that's playing right now is Nights into Dreams. It's awesome. Okay. So, yeah, let me just stop the music. All right, so thanks everyone for joining. Yeah, one of the things I changed since last stream is I actually got myself a proper mic. So hopefully the sound will be better. I listened to some of my previous streams and the audio was just awful. Mainly for two reasons. One was the fact that I was just using the mic that came with my webcam. And also because there was some interference from my other webcam for this keyboard cam here, which, you know, don't know if it's worth having this keyboard cam, but still, it's kind of cute. So anyway, I bought myself a proper mic. It's a blue Snowball. Here, I'll just show it on the camera. This thing. So it was recommended by a bunch of people online. It seems to be a decent intro level mic. I don't know if I tweaked it right in OBS, so if you guys have any feedback about the mic, do let me know. If it's, I don't know if it's too low or if it doesn't sound quite right. I don't know if I should bring it closer to me. Anyway, I'll just try it like this for now and see how it goes. So, all right, so last time on the last stream a couple nights ago, I worked on a bunch of stuff which I'd like to go through right now very quickly. So for those of you who weren't watching last stream, so let's go here to Vectrexy on GitHub, and we'll take a look at the commits I've made. So yeah, basically last stream, which was a couple days ago here, what I worked on was this here. Debugger, implement optional step count parameter for step instruction. So this basically was to add a optional parameter here to step so that I can type step and put a number and it will step that many instructions times. The reason why I need this is because sometimes, you know, or oftentimes I'm at the point now where the CPU will run for many millions of instructions, and I need to be able to say, turn off the trace, run a certain number of instructions, then turn a trace back on, usually like, I don't know, some few thousand instructions before a bug, a crash, or a search or something. So I'll do that, and then I'll turn on trace and I'll run. So that's why I added this feature. So that was really cool. And the other feature, which was even cooler, that I implemented last stream was adding watch point support. So watch points are also known as data breakpoints or hardware breakpoints. Basically, it's a way to say, you know, break into the debugger when a certain address is written to, like a certain value at an address, I mean, is written to. So that's what watch means. R watch is when it's read from. And a watch, which I think means all watch, is when both a write or read occurs. So I implemented all three, which is what this change here is all about. And it's pretty cool. So if I run my debugger now, hold on a second, let me run it in debug. So yeah, if I run the debugger, here we go. So here's the debugger. Let's just turn on color. Oops, I'll just turn on color because it's a bit prettier. So yeah, here in my help, I actually show, I added this line here. So set write read both watch point and an address. And just to show what that looks like, so I mean I can set a regular breakpoint on say address 0. So it says added breakpoint at 0, and I can say watch 1. I can say rwatch 2, and say all watch, a watch 3. Info break shows me the 3 different kinds. So here we can see instruction breakpoint at 0. Otherwise we have a write, a read, and a read write on 1, 2, and 3 respectively. And because I hooked it into the normal breakpoint stuff, I can also say disable 1 like that. And you can see it's cute. I color it red when it's disabled, and it's green when it's enabled. So basically that's what I did last stream. So now that I have the ability to step a certain number of instructions, to set these kind of breakpoints, I'm in a good position to debug the problem that occurred a couple of streams ago, where I run the CPU and it gets to a point where it tries to access memory that is in cartridge address space, which doesn't make a lot of sense. So here, let me show that happen here. So yeah, I have here a little agenda I was putting together for today. I'm not sure yet if I want to do this kind of turbo mode, so we'll see. But the main goal for me today is to debug this weird address range access, which is a load from effective address. Actually, it was this, but then I made a change where I don't load a cartridge anymore for the Vectrex. And now I actually get an access at address 0, which is weird because address 0 is in the cartridge address space. So let me just show you what that looks like. Let me get my usual things I like to put into my debugger when I start. So yeah, I load symbols. What else? Oh yeah, I set the dude register to FF, and I turn off trace, and then I just hit continue. We let it run. Now this takes a little while to run because it's actually emulating the Vectrex, the actual Vectrex speed. And right now, even though we don't see it, we're going through the normal boot sequence. We are actually, you know what? I'll show it. And this actually is the assert that I was talking about that I want to fix. But just to give you an idea of like about how far we are ostensibly getting, I can't actually prove it, but it's something like this. Let's see how this looks. So like the Vectrex turns on, you got this like these lines around here. Then it says Mindstorm. You can see here it's taking a few seconds. It says player 1, and then we get to here. And I think it's around here that we're crashing. I know that we probably are getting this far because there's a score that's being shown on screen here. Yeah, and this video quality is kind of awful, but anyway, there's a score up here that's like a 0. And I know that we're getting this instruction that's being called for, it's called BCD. Or no, sorry, it's adjust binary something. Basically what it is, adjust decimal, what is it again? AD something. Let me just check my opcodes here. Adjust. Oh yeah, that's it. Sorry, DAA, decimal addition adjust. I'm hitting this breakpoint, and normally this breakpoint is, this instruction is invoked and used when you're dealing with things like score, because you want to display an actual decimal number on screen. So that's why I suspect that we're getting this far, and also based on timing. All right, so what is the problem here? So the problem is, if we look here at the call stack, we're executing an instruction. In particular, we're executing a load into A. So that's what's happening here. And eventually we go and we say like, okay, I want to read the operand, and that comes into here and wants to read, eventually goes to the memory bus, which eventually goes into cartridge space. And the reason for that is that the address is 0. And that's weird. It's unexpected. I don't expect Mindstorm to be reading at address 0. And the reason for that is, if we look at the memory map for the Vectrex, So this is the memory map right here. It's kind of like all here on screen. So cartridge space in terms of the address space goes from 0000 to 7FFF. So that's the first 32K of RAM. So this is totally like what I expect to have if I actually load up a cartridge and start executing one. But that is not what I'm doing. What I'm doing is I'm loading up without a cartridge, which is to say the BIOS starts executing at F000, which is the last 4K of RAM in the address space, and eventually it goes into E000 range, so in the E range here, which is this 4K that is Mindstorm, the built-in game. So if Mindstorm is executing in here, I would expect accesses to be done in this range for certain data that's been statically put into the ROM. And I expect there to be reads being made out of RAM here. And also potentially reads from the VIA registers here, but mainly in the RAM space. And when I say mainly, I mean mainly these 874 bytes that can be used by the programmer. So anything that is a read outside of that seems suspicious and usually means there's some kind of bug still in my CPU implementation. So let's try to figure that out. So the way I'm going to do that is I'm going to come here to my debugger and I'm going to take a look at the instruction count. So this means that from the beginning we have now executed this many instructions. So I'm just going to paste that in here. And I believe I already have, yeah, it's this value here. So this, maybe it's not obvious, is about 2.2 million instructions. So I'm at 2.2 million instructions in. What I'd like to do is I'd like to get a trace. So what I'm going to do is I'm going to say, put this back like that. Perhaps the last, let's see here, 2000. So yeah, if I put here 70, let's get like the last 12,000 instructions in my trace. That should be useful. So I'm going to copy this value here. I'm going to restart my debugger. Okay, and I'm going to say, yeah, actually, I'm going to copy this first. All right, so trace has been disabled. I've got my symbols loaded. The dude register is set to FF. And finally, and maybe you know what I'll do is I'll add this in here for now. I want to step this many instructions. So let's do that. So this will just go ahead and execute 2.2 million or so instructions, and it'll stop when it reaches the end of that, or should anyway. Okay, so here we are. And now I want to turn on trace, and I would like to let it run. So without color, which will make it run faster. So there we go. So we're running now. And at some point, we're going to hit that, there we go. So now we just hit the same assertion as earlier, because we're accessing address 0. And here we are. So actually, it didn't flush. So yeah, so that's one thing about having no color, is that I'm not flushing. And because I'm hitting an assertion here, I thought I had come up with a, oh yes, that's right, I have an at here. So this is actually an exception, an out of range exception. What would be very helpful here, and I had started doing this earlier, is to actually trap this exception when I execute. So let me just go back to my debugger here. And we're going to come down here to execute instruction here. So this guy. So when I execute an instruction, ideally what should I do here? Yeah. So what I'm going to do is I'm going to say try. So let's try and do this. for now, I'm just going to catch any exception. And what will I say? I'll put a little printf here, and I'll say exception caught. With a little new line. I want to make sure that we break into the debugger. So what's my value for that? It'll be break into debugger, of course. Set that to true. So I'll do that. So this time, when it tries to access, it'll throw an exception. I'll bring it to the debugger, and that will actually flush. Oh yeah, it's saying not all. Yeah, so I need to return a value because it's the number of cycles that the instruction executed. In the case of getting an exception, obviously I'm not getting any cycles, so I'll want to return. Let's see here. This guy wants cycles t, so static cast to cycles t. Which I think is, yeah, it's a double, so that's fine. So let's do this again. So this time I'll actually copy everything here, and with a step, we'll run. Almost there, almost there. So yeah, again, guys, let me know if the microphone is better, if you can hear me all right, is it loud enough, is it noisy? I put a little noise suppression in OBS because I wanted to make sure that you didn't hear any kind of background noise, because in my tests, there's like a lot of ambient noise that's being picked up by the mic, so I put some noise suppression. I hope it's not too powerful, or maybe it's not powerful enough, I don't know. So any feedback on that would be appreciated. Okay, so we're here again. I'll turn back trace. I'll run, and this time we should break back into the debugger when the exception occurs. All right, exception caught. So, I mean, it's not super useful. It'd be nice to actually know what the exception is, etc., etc. For now, it's totally fine. I don't care. I'll deal with cleaning that up. I have plans for making the debugger, you know, like throwing useful exceptions, blah blah blah, for the debugger. So for now, it's good. We know what it is. There's an access. In fact, we even see it here that the effective address on this instruction, the load a u plus, is 0, and that's an invalid read, and so I suspect that there's something wrong here. So let's see if we can figure this out. So what I'm going to do is I'm just going to copy all of that and paste it into Notepad++, just so that I can do some searching and marking up and stuff like that. It's a little bit easier to debug problems this way. Okay, so let's start with what's going on here. So what's going on is that the U, which is the user stack register, has been set to 0, or has 0 in it. Now, does that make sense? Let's take a look. So actually, U is being loaded with 0 here, so that's interesting. So okay, load U 0, load X with F101, load B with this, and then we do load A, no offset, U, and then increment it. Trying to think, why would this code be doing that? So, I mean, I'm just going to go up a little bit here, a bit higher here, because what I'm noticing is that we're actually in the middle of a BIOS routine here, and this is why I load symbols, is that we actually can look at the BIOS code. It goes up a little bit higher here. We have this jump to subroutine DP to C8. So if I go here to my BIOS and look for that, this is it right here. So this says, oh, actually, let me go back here. Oh, no, there's an RTS. So actually, that's not the one I'm interested in. Let's see here. Is there any other RTS? Okay, so let's jump subroutine. Let's go a bit higher. Load A, decrement, load A, bit B. I just gotta find like a jump to a subroutine. Here. Might be this one. So draw pat VLA. So let's see, draw pattern VLA. So let's see what that looks like in here. All right, all these routines draw a series of pattern vectors. Yes, I think I looked at this one before. So it says the pattern to use must already, oh, hey, sorry, I just like missed the chat here because I had this window covering up. Gigant Fusion. I don't know if I'm saying your name right. You're saying the voice volume is perfect for me. All right, thanks, man. Thanks for the feedback. That's great. I'm happy to hear that. If you listen to my old streams, it kind of sucks. So I'm happy to hear that. All right, so all these routines draw a series of pattern vectors. The pattern to use must already be specified in C8 to 9. When using drawPatVL or drawPatVLD, the number of vectors to draw -1 must be specified in this address. Okay. And when using drawPatVLA, the number of vectors to draw -1 must be passed into the A register. Okay. Right. I love how, because I don't have a lot of assembly experience. I didn't write any like assembly when I was learning to program. I started in like Pascal and then C. So I don't have like a lot of experience with this. So when I read this code, I'm like learning strategies and of how people did stuff. And like one of the strategies I see a lot in this BIOS, and I'm sure it's like a common thing in assembly, is that you can kind of like do overloads of functions by providing these different entry points. And like, for example here, this is kind of smart, right? They're saying they're going to look at this address for how many patterns to draw, how many vectors to draw, sorry, -1. And they're saying normally they'll just read out of C829, but if you use the one with A, which is the first one it jumps to, it'll actually store the value from A into C823. Sorry, yeah, so C823. And then later on, it'll read back from C823. So that's like just a clever way to overload this function and reuse the same code. So I suspect it's totally the way it's always done, but I think it's kind of cool. And like here, they say that there's VL and then there's VLD. And the difference here is that if you use VL, it does this load D from X. So it's saying that this guy here means I'm going to get the value out of X and put that into D. Otherwise, if you already put it in D yourself, then just call this guy here. So that's cool, right? It's the same idea. So if you want to use the one with A, or the one that comes from X, or the one that comes from D, this is how you do it. So pretty interesting. All right, so let's see if I can correlate what I've got in the BIOS here with what I've got in the code here. So we've got this jump here, and then we execute a whole bunch of code. Eventually we call DP to C8, so I should see that in here. A lot of code. Where is it? Store A, clear, load effective, inc, store B. Wait, there's an RTS there, so maybe I'm wrong. Is there an RTS in here? Okay, so actually that's not the function. It's just a bit annoying to figure it out. So this is a function that jumps and then returns. So actually then we go back to some outer function. So I gotta keep going up. That's another JSR to RTS. Here is that. Okay, so it might be this. Move to IXFF. So let me see now. Go to the BIOS. So here's another BIOS routine. These routines force the scale factor to FF, 7F, or the A register, and then move the pen to the YX position pointed to by the X register. The X register is then incremented by 2. So is this our friend? It doesn't look like it. Oh yeah, maybe. Because then this drops down into here, which drops down into here. Okay, so let's see if I can figure out what's going on here. I'm gonna split this guy out. Oh, how do I do that again? Move to clone to other view. Actually, I just don't want to clone it. Oh, I guess that's fine. All right. So let's move to IX. Load B. Load D. That's here. Store A. Push. Keep going. Keep going. I see the jump subroutine ABS AB. That's over here. That's the one we saw before. So we run all this, then we come back, and then there's a load A. Or not. Jump to subroutine, ABS, AB. Oh, sorry, there's the RTS for that guy. Okay, followed by store B, or A, all that. Compare, BLS, compare. Branch if less, okay. So we did branch to L345. So then we do another bit B. So come down here, bit B, branch equal, then return. So actually this isn't even the one, because this RTS goes with a jump up here somewhere. All right, let's see if we can figure it out with this guy here. Reading assembly is fun. You know what it is that I'm missing? I'm missing a call stack. That's another feature I really need to implement, because if I could even build a call stack with these jump subroutines. I even have these symbols here, so I could show the symbols in the call stack. That would make it so much easier to know where I am. Especially if I'm in a BIOS routine. Okay, but let's just see if we can figure this out. So this is move IXFF. Draw pat VLA. So that's the pattern one that we were looking at before. You know what I'm going to do? I know. Let me look for no load A U plus. Yeah, but it might not be exactly in that format here. Just try and find something that I can hook onto. Why am I not finding this? By the way, is that audio from Windows too loud? You know, like when I do this? Do I need to lower that? Because I had a complaint about the audio output being too loud from Windows. So let me know if that's too loud. No, it's okay, says Gigant Fusion. Thanks, man. All right, so what is going on here? F07A. Okay, let's try LF07. I mean, the fact that I'm not even finding these in the BIOS is a little disconcerting and makes me feel like, you know, what's going on here, because it's a bit strange. F06F. Okay, I feel like that would be somewhere in here. F06C is warm start. So am I in here? Load A, yeah, here we go. Warm start. Jump here to restart the Vectrex without reinitializing the OS. That's interesting. All right, so let's see. That's really close to where we are. So we're doing this. Store A. Okay. So here it says store A 29, but actually that's a direct page relative instructions, so ends up evaluating to vec pattern, which is what we see here. What I've noticed is that whenever there's this little left angle bracket, I think that means to the assembler that you want a direct page relative instruction. So it's saying, like, you know, use a direct page, and the value in the program counter here to get to that value. So okay, so that's store A, load D. I mean, sorry, what it means is that it's supposed to take whatever is in the DP register and take the, like, compute an offset. Is that right? Vec pattern. C829. So yeah, it's basically telling the assembler, I want you to compute, you know, an offset that is just 1 byte from the current program counter, so that it's compacted nicely. All right, so let's go back to where we were. So this is let me just make this bigger. Look at address 0. Oh, there you have it. Check for valid cartridge. So we finally found the bit of code. I've been wondering about this. So I was wondering, like, how does the Vectrex know that it's so cool. Like, how does the Vectrex know that it needs to run from the cartridge, or does it need to go to Mindstorm? And you know what? We found the code right here. This is super cool. What it does is it says, all right, let's like load into you the 2 bytes at address 0, and then saying, you know, load the copy write string into load X, into X, I mean. And then it wants to basically see if the copyright string is there. And so it's really cool. Like, here, let me show you what copyright string is. Copyright string. Where is this guy? Isn't it in here? Find all in current documents. Oh, here it is. So the copyright string is GCE 1982. So it's looking for this exact string at that address, which is actually the exact string that must be at the beginning of the ROM. So like if I show here in Scramble, I'll just open it in here. You can see that that's exactly what we have at the beginning of the ROM, right? So that's pretty cool. So, okay. So that means then that this loading from address 0 is not a bug. It's completely normal, and it is exactly where it needs to be in order to figure out whether there is a cartridge or not. So I just want to take a little note of this because I've been wondering about this, and now I know what to do. I think it's pretty obvious. So I'm going to come here in my notes, and I'll say BIOS routine, what's it called? Warm start? Yeah, BIOS routine warm start, which is at F06C, is where the BIOS will check to see if a cartridge is loaded. It does this by, I'm just gonna put a little wrap here. It does this by checking if the copyright string is at address 0. Cool. So what this means is that if I don't load a cartridge, I at least need to allow an access to address 0 in my cartridge code. And in fact, let me just look at it again. Do I need, like, does it need to be even longer than that? And I guess it's going to fail as soon as it checks the first byte, right? It's going to actually load up the copyright pattern, and then it's going to start looping. It's going to look at 0. It's going to say, sorry, here, compare next byte. If it's a match, good. Not okay if the last byte is wrong. Branch if equal. Bad cart, load Mindstorm address. So I think I only need basically a read from 0 to be okay. So let's see if that's true. Thinking, like, what's the right way to do this? I have two ways I can do this. I can either special case a read from 0, which I think is not a good idea, or, yeah, what I'm gonna do is whenever the cartridge is initialized, I'm just gonna go ahead and reserve, resize, not reserve, resize to 1. And what happens is if we do load a ROM, that's gonna get completely replaced. So we'll just, you know, this little heap allocation will just disappear. So I'll just put a note here. Need to allocate byte, 1 byte at address 0 so that BIOS can check that no cartridge is loaded here. Is loaded. So in fact, instead of that, I'm going to do this. I'm going to do a push back, and I'm just going to put 0. That's even better because I want to make sure that it gets a value of 0, right? Okay, so let's compile this. So what this means now is I will pass this access to 0. I should. And we'll continue running, and we'll see if we hit what's like the next invalid access that we'll hit. Don't think I need this. All right, don't need this. Let's go back to my, okay, so I'm not gonna need to step that many times again. Let's launch the debugger. And we'll just continue, and I'll take a drink of water because I get super thirsty when I talk all the time. All right, excited to see where we get. And every time I'm waiting like this, I keep thinking, I need to put that turbo mode. because then we wouldn't wait this long, right? We just execute the Vectrex CPU as fast as possible. So it's pretty cool, running for a good while now. Oh, actually, yeah. What's going to happen is if I do get that out of bounds access, I'm not going to know because I don't have that exception anymore. I mean, what I have is now is I'm going to catch that exception, and I'm not going to know exactly where that was. What I need is really for my debugger to break on that exception. So this is what I'm going to do. I'm going to do two things. For now, I'm going to disable this exception code. And let me try just like a little hack to make this run faster. Because see here, I'm actually setting the frequency of the CPU, right? So like, I'm just going to put like, what's it called again? Integral constant double max, something like that. Did I get that right? No, it's not integral constant. What is it again? Numeric limits. That's what I was thinking about. Numeric limits of double max. So let's see if that actually goes faster now. That really should just like run an infinite number of a huge number of cycles. I think that makes sense, right? Yeah. Just thinking about it. Okay. Okay. Copy this and run. No, yeah. Okay, so what's going on here? Still taking a while to run, which is surprising. I mean, I suspect that we're in the middle of here, so let's just double check, put a breakpoint. Yeah, we're here. How many cycles? Look at that, huge number. I mean, actually, you know what? That's kind of dumb. I don't want to put something that I then multiply by delta time, and I think cycles t is a double as well, so that doesn't make any sense. I just need like a really large number. So like instead of 6 million divided by 4, let's put like, what should I put? Maybe float max? Haven't given this too much thought, but something that when multiplied by delta time, I don't want it to overflow. Yeah, I don't know. What do we got here? Well, that's a huge number. Yeah, I'm like really surprised. I'm surprised that it's not breaking yet. Let's see, how many instructions have we run? Oh, not that many. How can that be? Execute instruction. 3 million. Now we're at 4.5 million. Okay, well, I mean, we're definitely past the 2.2, but it feels like it could run a lot faster than this. So there may be a few things going on here. I know that I dramatically slowed down how fast it can run with the watch points that I added. Every single read and write, it's checking to see if it's in a map, if that watch point is in the map. So that's definitely not fast. So maybe that's what we're hitting here. We're at 7.4 million. The other thing I can do is I can run and release, which is faster because I'm in debug right now. Okay, this is way too long. Let me try in release with debug information. That's the problem with this early stage in development, is that I'm basically going at it blind. Once I have some graphics implemented, it's going to be easier. Okay. Oh, and there we go. Exception caught. Exception caught. I thought I took off that exception. Oh, I took off the wrong one. Yeah. I wanted to take off this one. Okay, so let's see. So yeah, it's like insanely slow in debug, but in release it's so much faster. There we go. Wow, insane. And just to see like how many instructions, 10 million. So that's impressive, right? Like it took seconds and seconds running in debug to get to like 4 million, and here in less than a second we got to 10 million. So that just goes to show like the scale of optimizations that's going on here. All right, so this is a read of which address? I don't actually have it here. Let me see if I can figure it out from looking at this assembly. Control, what again? Control Alt D. Okay, so this is the interrupt 3, so that's the assertion. Call X range, cartridge read. In fact, no, that's it. I'm not going to see it there. Okay, yeah, two things. What I'm going to do is I'm going to come here to the debugger and take note of this instruction count. And I'm going to put back my try catch because I would like to actually see the instructions around it. Bring this here. All right, let's run this again. All right. Okay, so no, actually what I need to do is I need to step near here. So we can see here, you know what? I actually think this is the bug from a few streams ago. So this is actually encouraging. I'm gonna run up until here. I'll give myself 6,000 instructions for the trace. We'll run again. So we'll do that, and then we'll do a step of that many, like that. Okay, so we've reached there. We'll turn on the trace, and we will run. Okay, and here we are. So exception caught. And in fact, the line just before is showing us the error. So let me just double check, because I think this is exactly where, yeah, I think this is exactly where I was a few streams ago. So we're back to the original problem that I was trying to figure out. So let me just double check. This was the trace I had. Yeah, we're loading 3408 into X. There's 3408. In fact, now it's 3409. This is at F410. So actually, so it's not the exact same location, but it's like around the same thing, interestingly. So here, let me grab that, put it here. And okay, I'll close this. So that's the new one, and this is the old. So F4. Yeah, like super similar. The only difference here is right at the bottom. Load B1S, load X2, S. Oh, it's there. Okay, and then jump subroutine to draw VLPB. Store B. Oh, okay, it's just that I'm getting one more line. So this is the exact same thing as last time. Fantastic. Store B04. It's just because last time when I was getting it, I didn't get the print of the last line because I didn't have the exception, etc., etc. So this is good. This is good. And yeah, it's still 3409. So that's exactly where I was last time. And I had made some note here of what I wanted to figure out, which is up here. Yeah, so I was kind of like, let me refresh my memory a bit here. What's happening is we're trying to read in memory from 3408, and that's weird because that's in that cartridge space, right? The first 32K. And what we see here is this is Mindstorm. Unfortunately, I don't have the code for Mindstorm. That's not part of the BIOS here. You know, when it figures out that we're in Mindstorm, it just says, all right, load up E000 and into U, and then what? Prepare to play the game. So yeah, it's just saying, okay, that's it. It's just treating, it's either going to be at 000 the game, or it's at E000, and then that's it. I don't have the code for that. This is the BIOS. But anytime we see this E here, we know we're in Mindstorm. And Mindstorm, for some reason, is trying to read from the cartridge space, which is wrong. Why is it doing that? And the place that it's getting that address from is here in X. No, sorry. It's basically in the stack plus 2 bytes. And if we come up here, here is where we push to the stack those 2 bytes. And if we come a bit higher, maybe we're supposed to store a plus x to x, not read what's there. No, that's not true. I had already figured out that that was not the case. Here I said, look for push U above to see where 04 got pushed there. Explicitly loaded into U. Look for push U above to see when 04 got pushed there. Is there another one up here? No. Okay, so here. So E262 and E263. That is the memory locations where 3408, the invalid address, are being stored. And this is a weird address for where the table of values for draw VLPB should be. I just want to see, why did I say it was these 2 addresses? Okay, we can see it here. It's loading into X at E25A plus 8. the value that's there, which is 34, that goes into X. And in fact, because it's loading into X, it's loading 2 bytes. So it's the 2 that are there. We only see 34 here, but we know that we get 3408 because later on when we actually push X and then read from the stack at that offset, those are the 2 bytes that we see, and that's what we're getting our invalid read from. So the question is, why are these values being stored at E262 and E263? So to answer that, I need to put a watch point on these guys. So let's do that. So I'll start with one of them. And I'm not sure like when I should put it and all that, so we're gonna have to mess around a little bit with it. Actually, I'll put it on both. So I'm gonna put a watch on this guy. In fact, yeah, it's a right watch. And on the next one. Like that. Let's do this. So we'll restart the debugger. So here it is. Okay, so I've got my 2 watch points. There we go. Wait. No, I made a mistake. So delete or remove 1. What was it again? Delete 1. Delete a breakpoint there. And watch instead this guy. All right. Info break. There we go. 2. I don't understand what just happened. Okay, that was like a super weird bug. Okay. So weird. Like over here it was 262 and 264. I deleted at 1, which should have deleted this guy. And then when I oh, okay, it's this weird line where I did watch. It somehow interpreted this guy as this address. That's so weird. Okay, anyway. I mean, I don't have like super awesome error checking here in my debugger because whatever, right? It's just for me. So, okay, as long as it doesn't crash and stuff. I've got my watch points. So let me just run. Let's just see what happens. Oh, crap. And I got an exception caught. So that is interesting and surprising. Surprising because, yeah, that doesn't make any sense. Does it? So what that would imply, if my watch point is working, what it would imply is that in fact those values are already in the ROM. And I can figure that out if that's true. Yeah, I can figure that out. So let's take a look. Okay, so let's go to the BIOS ROMs right here. And I'm gonna use, I like to use this, do I have it somewhere? Maybe I don't. Maybe I didn't install it yet. So I'm just gonna install my usual hex editor, XVI 32. It's super old, but does the job. If anyone has a recommendation for a better one or one that's better, I guess. But this one seems to do the job for me. So where is it? Extract. Okay. All right, here we go. So let's drag the BIOS ROM onto here. There we go. So like Mindstorm is right here at the beginning. And I mean, I don't know if this font is tiny now. Probably is. I don't think it's easy to zoom in here though. Yeah. Not sure. Maybe the font or something, appearance. Oh, here we go. If I make this like 14. Wow. Okay, that's pretty good, right? So there are all the bytes at the beginning, Mindstorm, etc., etc. So let's see if we can go see whether those bytes really are at that offset in the ROM. So E262, so I'm really looking at offset 262 in hex. So we'll go to 262. And there it is, 3408. So the watch point, either it's working or whatever, it's just, that's not triggering because there is no write there. It's actually just reading from there. Actually, I should have known that. It makes total sense because it is reading from an address in the ROM, of course. Okay, so what does that mean? That means I need to rethink what's going on here. So does it even make sense that we're reading from these addresses? Maybe the problem is that E25A is incorrect. Maybe this is wrong, this offset. What could be interesting actually is to break at E59F. Like maybe this, because this is a, I wonder if we hit this address multiple times in Mindstorm, or is this like the first time we hit it? Maybe that can give us a hint of what's going on. So let's try that. So what I want to try and do is forget the watch. Let's break there. So here's our breakpoint. Turn on trace. We'll step. Okay, see, that's interesting, right? So this one time here when I'm stepping, I'm reading at E25A. So if we go back in here and we actually go to E25A, so that's 25A, we're here, EE3D. After that, it's EE53, EE6F, EE8E. So those are all valid addresses in the ROM space. But then there's 3408. So my gut tells me that what's going on here is that the CPU would read 1, 2, 3, 4 times, but should not be reading from here, probably the 5th time. So let's see if I'm right. So we just loaded that into X, and if we look at the registers, X has EE3D. That totally corresponds to the EE3D we have here. Let's continue. I'll turn off trace. Should I turn it off? Yeah, I'll turn off trace. Okay, so we hit it again, turn it back on, and let's step it. Okay, so that once again we're reading at offset 0. Okay, I'm gonna run again with trace. This time I'll just leave trace on. I don't know how long it takes. There we go. Step it. Again, it's at offset 0. Again at offset 0. And here we are at offset 8. And now this is the one that's gonna cause me a problem. So that's interesting. So we did what, 3 or 4 loads when it was offset 0, and then this time around we're at 8. So my feeling is that the problem has to do with what's in A. With what's in A. So what's in A comes, we can see it a few lines above here. What's happening is it's saying load into A 1, comma U. So that means user stack pointer plus 1, which resolves to this address, which has the value 4. And then we take that and we do a logical shift left A, or arithmetic shift left A, same thing. So we shift it by the bit. This is 1 bit that's turned on, and we shift it left, and that becomes 8, because shifting left by 1 is multiplying by 2. And that's where we get our 8 here. So I'm interested in comparing this to the code we had above. So let me just grab all this. Okay, I'm going to take it and I'm going to clone to other view. Like, are we doing something similar when we hit this address above here? Oh, did I not grab all of it? Oh, yeah, okay. That sucks. It's because I'm running in release, so this version, oh, that's a pretty big buffer size. What happened to my buffer? That doesn't make sense. This is where I don't like the way Windows works with commands and like remembering settings and stuff. You have this concept of like default, and or you can change the properties of this specific instance. It's a big mess. Yeah, it's not taking my it's not taking my options, and the reason I know that is because I have to keep dragging it here. And when I look at the properties, you see how it says Windows position -1746? That means it should have opened on this screen relative to my primary monitor, which is off screen. So why is it doing that? I know it's in the registry. Try again. Okay, so maybe now it'll work. To know, I'm just gonna run it for a while and just see if like I can grab. Does the scroll bar really, like, I mean, does it really keep 99999? It doesn't look like it. Oh no, it does. 9999. It's just that it's not enough. Okay. So it's okay, because I think I can get enough from just doing a couple of grabs now. So I'm gonna come back to, where was I? Here. Copy, paste, run. We're here, we'll turn on trace. This is the one where we got 0. just continue. We got it again. Continue again. Continue. This is still a good one. This is the one with 8. So I'm just going to grab this. There we go. So now I have 2 that I can compare. Okay, so one up here and one down here. So what does this look like? Didn't I just get 2 of these? $637. What? Oh no, sorry. Wrong view. All right, here we go. Okay, so see here, in the case that's not good, when I load from U at offset 1, I'm getting a value of 4 that's been stored in C934. Okay, yeah, this is good. And here I'm getting a value of 0 from the same address. So now what we're seeing here, and so this address, C934, this is RAM. So that means that it's writing this value to here somewhere. I don't know if I have it in my buffer. No, but I can put a watch point on this and see when that value gets written to, and there we will find some more information. So let's do that. Where's my guy? Here it is. So watch, whoops. Copy, watch this guy. So we'll break there, we'll watch this. I suspect we'll hit the watch before. So let's see what happens. Honing in. So there's my watch point. No, sorry, invalid command. I have to write watch. There we go. All right, so continue. Watch point hit. Right value of 0, which makes sense. So where are we? We're at E01B when this occurs. You know what I'm going to do? I'm going to turn on trace now because I know that we are within Mindstorm and this is going to happen again. So let's run. And there we go. We just hit the watch point again. So we're in this bit of code here. So what's going on here? Here we've got a clear at X plus. In fact, we're in some kind of loop here. What's this loop doing? It's going through a whole bunch of addresses and clearing them. Okay, I think we're just inside some massive loop where we're just clearing all the values in RAM. So I'm just going to continue and we'll see what that looks like. Yeah, it did end. Okay, so we're still running. Yeah, so that was just a massive loop that, you know, probably at the beginning of Mindstorm, it just says, let me clear all my RAM, and then it starts running. This can take a little while. I'm considering just, because I know this goes a few times, I'm going to stop. I'm going to turn off trace. Okay, so we hit our watch point. Now I'll turn on trace. And I want to take note, when we hit our watch point, actually we were in F8 B3. So I'm going to take a note of that because that is actually a BIOS routine. So cleared, this was cleared to 0 at F8B3. Specifically, no, actually at watch point hit, right value of 0. So usually when I hit a watch point, we do execute the instruction just before. Oh no, that's it. I don't know what it is, so that's all right. Okay, and now I've got the trace enabled, and let's continue. Hopefully we'll hit the next write soon. It's incredible how much slower it is when the trace is enabled. And this is like buffered output, so it's actually a lot faster than it used to be, but it's still super slow. If I find this really too slow, what I could do is the same trick I was doing before, is like note how many instructions have passed, and then we'll just step to that many with some offset before, and then we'll trace from there. So I'll just let it run just a tiny bit more. Yeah, I'll even hide it. Take a peek. Okay, this is just too long. Turn off trace. Okay, so we hit a watch point again. This time, different place. So I'm going to say cleared to 0 at this guy. Interesting. Okay, let's continue again. Once again at the same place. Watch point hit, and we're here. And I mean, I'm saying at, we could be, it could be the instruction just before it, but it's close enough. Continue. And now we've hit the breakpoint at E59F. Oops, I wanted to turn on trace. Okay, turn off trace, continue, trace, step. So that's it, so it's 0, trace, continue, trace, step, there's a 0 again, trace, continue, trace, step, trace, continue. Aha! Another time it was written, and this time we are again at E9D9. So this really seems to be the place. We're really close to what's going on here. It's at E9D9 or whereabouts, where 0 gets written there. Okay. Sorry, continue. So it's actually at E9D7 that it occurs. I think now I can leave the trace on because it looks like we're very close to where all of this is happening. What we see here is saying store 1, U. So it's saying C933 plus 1, which is C934, which has the value of 0. C934, which is what we're looking at. And we're saying store U plus 1 there. Store A, sorry, store A. And A has 0 in it, and it's getting that from here, load A in what's at S, which S is the stack pointer, which is CBDC. Okay, just take a snapshot of this. I'm just going to write down what this is. Okay, so this is the case where 0 is written to C934. All right, let's continue. Aha! And this is where 4 got written to C934. So these watch points are awesome. So useful. So what is this? What is this? This is actually a load A of 4. And then writing A. And A actually came from the stack from here. Pull S. I'm just noticing here that there was a pull from the stack here, and then another pull from the stack here with an extra register. So that seems a bit strange, because there should be matching pushes for that. What is going on here? Okay, well, let me take this then. Getting closer. This is where we write 4 to C934, which is probably incorrect. Okay, so let's see if we can't figure out why this is happening. I mean, we are loading 4 into A. So no, it's not coming from the stack. We really are loading 4 into A here. Hey Simon, how's it going, man? Thanks for joining the stream. I am... Oh, you're racing shortly? Well, I'm actually streaming myself. I'll be streaming probably till about midnight, so maybe I'll catch you after that. Simon streams himself doing Zelda 2 randomizer races, which are pretty cool. He says, it's elimination. If I die, I'm done. Aw, man. I hope you win. Best of luck, dude. Okay. So just thinking about how we load 4 into A here. I wanted to kind of compare that to the case was cleared at E9 D9, and then here I want to say that $C934 set to $4 at E717 at EC17. So what? So what? Why? Is it wrong? I'm looking here at, there's a return from subroutine here, and then we have this pull s, like, so one thing is, yeah, so here, pull into stack, pull from stack, I mean, B and PC. Okay, so that actually changed the program counter. But since this is in the BIOS, should I be surprised that it does this? Because like here, after this instruction, we end up here, back in Mindstorm. It just surprises me because normally BIOS routines, you use JSR to jump to them, and then return from subroutine like here. But then here we have another way of jumping, which is basically saying, oh well, I pushed the program counter on the stack, so I want to pull it from the stack, which makes me question, is this really true? Is this really happening in the BIOS? Let me just take a look. F60E. Just gonna lower the volume for myself. Okay, so no F60. See, that's interesting. F67. LF6. LF637. But no LF60. Let me see, up here. Maybe we're over here. 63. Yeah. Oh, there it is. Okay. Restore run value and return. So yeah. This surprises me. This guy right here. Pull from the stack, B, and program counter. So the RTS that's right above it comes from this BSR xform rise. So get the rise value. What is this guy here? This routine takes an angle value and calculates the rise and run for that angle. Wow, that's pretty cool. Keep in mind that most games store x and y coordinates as 2 bytes each, with the upper byte being the actual coordinate and the lower byte being that which is usually added to the rise run value. When the lower byte overflows into the high byte, then the object will move. The rise run values returned here are meant to be added to the low byte, not the high byte. Entry DP. So I guess this is just like a, maybe it must be like a common technique in this assembly language where what? So it knows that xform rise will push to the stack the return value into B. So let me see if I'm right. Why does it say A reg? The transformed value is returned in the A register. Okay, so that does not add up to what I was looking at here. Get the rise value, restore run value, and return. Oh, okay, sorry, rise and run. So a reg. So a ends up with, so here we push a onto the stack. So basically when we enter here, the return value is on the stack. Then we push a, which is the rise value. The run value. I keep saying the wrong thing. Save the run value, which is in A. Get the rise value, which will now be in B. So that's good. No, sorry, it will now be in A. This guy stores it into A. So that's what we want. And then we say pull S, B, PC. So that means that we're going to get the run value that was pushed here into B, and we'll also get the return address and store it into PC. So this is kind of like a shortcut. Instead of doing like pull one value into B and then do an RTS, we're doing both at the same time. We're saying pull B and RTS by pulling PC. So there's some kind of shortcut. Okay, so that's perfectly fine. Nothing wrong there. Okay. So we're loading 4, then we're storing 4, here, and now if I continue, we hit the breakpoint, and like this is where basically, you know, things go wrong, because when I step, this is where we've got the incorrect or seemingly incorrect offset. Because there's the read of 4 that was written to C934, and then we shift left. Just thinking about this logic. 4. It's just funny because where's my XVI? Did I close it? No, it's here. So this would have been like plus 2 bytes, plus 3 bytes, plus 4 bytes. See, like 4 bytes would have still been a valid place. 6. Wait a minute. 2, 3, 4. Wait a minute. One, 2, 3, 4, 5, 6, 7, 8. Okay, yeah. So yeah, 8 bytes gets us here, 6 bytes here, 4 bytes there. Like, what's with that? What's with the shifting left? Okay. Just wanted to get the rest of the trace. So that's where we hit the trace point. And then we continue to run. Seeing if there's anything that stands out here. Whole bunch of stuff. The VIA registers. Then finally intensity 5F, so we're going back to the BIOS, come back, and then here we are again, loadx E25A, get that value 4 into A, and we shift it left. $86.04. Yep, definitely a load A with the immediate value 4. Yeah, this shouldn't be load index register. I don't know why it says index here. Should be accumulator. Okay, so unless U is wrong here. I mean, if it shouldn't be 4 written stored there, maybe U is wrong. Because here what I see is we're actually pulling from the stack here a value into U. I mean, it's kind of interesting, right, that there's a U here, but there isn't one here. I've gone over my pull instruction, but I'm going to go over it just one more time, make sure that this makes some sense. It's 35F6, 35B6. So there's a, okay, let me see here. Because, I mean, maybe U, because I'm looking above here, right? Like, U used to be C933. Oh no, it's still C933, even after we pull it from the stack. But maybe that's wrong. Yeah. Why? That's interesting. Seems odd that we would pull the same value, right? Okay, that's my next suspicion. Maybe my pull S, because, yeah, this could very well be the problem. All right, let's check it out. So here is the pull instruction for S. Yeah, I was thinking about this like little special case garbage here. That's like, if I passed S, then I want U. I want a reference to U, otherwise I want S. And then I want to pop 16. Okay, let me debug this. So I'm going to put a breakpoint on EA3C. Let's just go for the gold without the trace. Okay, breakpoint at EA3C, info reg. So the stack is at CBDC, and U is C933, which is the C933 that we see here. And we're about to execute the pull S instruction. So I'm going to put a little breakpoint right there. I am in release though. So missing debug symbols here, so this might not be awesome, but let's just see what we get. All right, so there's my step. And okay, so let's see, we read the value. So I'm getting A, getting B, X, Y. So I am in here. See, I can't tell. About the pop value, can I get, okay, S and U. C933, CBE2. It's really tough to know. Compare EDI to EDX. Push EDI. Does this make sense what I wrote? Basically what I'm trying to say here is, because the way pull works is that, because I'm reusing this operation for both for both pull S and pull U, and the trick is that I pass S or U to it. And the pull instruction, if you're pulling from S and you set a certain bit that says I want the stack pointer value read, if it was from S that you're reading, then it means that the target is U. If it was from pull U that you were doing it, it means that if that bit is set, it's S you're supposed to get. And you can never have both. You can't have both S and U, obviously, which it would make no sense. And so the way I handle that is I say, like, if the stack register that you passed in is S, then you must mean that you want to write to U. And so this is supposed to be a ref to U or to S. And then I'm supposed to be writing to that reference here. Okay, let me just see if I step here. Does that change anything? Actually, let me go into pop. I got high and low, and I don't have values. Okay, so it actually returned 5.1. So it returned C957, which U got changed to. But C957, but that's not what I have here. C957. I do have C957. So confused. C957. Okay, so I'm hitting this breakpoint multiple times. I was under the impression that I was only there once. C933. Very interesting. Okay, so I'm hitting this multiple times, and in one of those times, it would look like I'm pulling C933 again from the pull S, which seems so unlikely. Okay, step. So another case of, oh, look at that. This would be the case, I think, where we're going to go wrong now, where we did a pull S, and this time we ended up with C933. So one thing I can do is, let me just check something here. 1, 2, 3, 4, 5, 6. So 6. So that's right. 1, 2, 3, 4, and 5, 6. 7th byte would have been U from when the stack was pointing here. So let me print $CBDC DC DD. Okay, so here we can see that, yeah, DC was 0. That went into A, which is the pull S A. At the next address, the next byte, FE, which is for B, went into B. The next 2 bytes should be an X. So E and F 090, yes. That went to X. The next two, so that would be E0 and E1. C9OB would have gone into Y, yes. And then the next two should have gone into U. So CBE2, E3, C933. So yeah. So that's interesting. Okay. So that's not the bug. So C933 was actually on the push to the stack. Trying to see if I can figure out where that is. Maybe it's the push. That's wrong. From here, let me look for push S. That's cool. I just recently updated Notepad++ and I just realized they used to have like a checkbox for search up, but they now actually have a button and they say use Shift Enter to search in the opposite direction. So that's cool. That's interesting. Push A, B, X, Y. Weird. So usually when you have a pull, you have a matching push, but starting from here, we have a push A all the way up here, which is not even that far away. 9212. Otherwise, we have to look for things that are modifying the stack pointer. It's so weird. Push to SA. Oh, okay, sorry, just another pull there. But even this is weird. Push SA, pull SB. Oh yeah, that's that code we were looking at before. I guess it's possible. Okay, so these go together. I don't know how to, here, I'll try to do this. So let's look for another push above. Let's push SX. So is this push? Is there a pull? Another one of those pull XPC to return. So these go together. And here we have a push ABXY, and I think that goes with the pull ABXY here, pull ABXY PC. Which one did I just use? $? No, %. Okay, so then the next one should be more interesting. Or not. Okay. Pull, pull, push, push. AB, BX. Yeah, so these go together. Like running out of characters here. Whatever. So AB. So not those. Okay, here. So okay, there's another push. There's probably a pull for that guy right there. Yeah. This is the one. Or no, this one. This one right here. E9A1. Okay, so this is the push that corresponds with the pull where you had C933 in it. This is where U is pushed with C933. Okay, and I mean we can actually see here in my debugger output that indeed U is C933 here. Oh man. So it was C933 for a long time. Oh, CAD1 here. C933 here. Oh, I think it's because I'm a missing trace. Because here the trace was disabled. Sucks. So I don't actually have the code where U was U became C933. Thinking. It really sucks that I'm missing this code. CAB1, CAC3, CAD5. And then at some point, and what I'm going to do is what should I do? What should I do? .d. Let me try something. Trace disabled. Here, let me just break on this guy. Load my symbols. Okay, turn on the trace. Let's just run. C933. C933. Oh, C945. C933, C945. C957. Very interesting. Oh, 6-9 now. You know what? I'll be right back. I'm just gonna go to the washroom, get some more water. So I'll be back soon. All right. Oh man, this is still running. Will it ever end? Oh man, I don't understand. It's just, I'm thinking about this problem and it doesn't feel like it's doing something wrong here. I mean, so what? If it pushes U with C933, I mean, that seems legit. Just looking at this here. Just thinking about this here, like C933 with an offset of 8, isn't that where we're having our problem? No, okay. It's not that, it's at C934. Okay, over here, it's just offsetting 8 from C933. And then here it's writing, so the problem is that it writes 4 at C934, which then later on, when it loads that 4 back here into A, and then does a logical shift left of A, which doubles it, becomes 8, and then we're off addressing what seems to be an invalid value in this ROM. So there is one thing that's possible. It bothers me to say this, but like, it's maybe this is a bug in Mindstorm, and that it would actually read at this invalid address, and because there's no cart there, maybe the Vectrex was returning 0. Maybe. That's entirely possible. It's within the realm of possibility. Like, come back to this here, like so this E25A, this like base address here, right, that gets loaded explicitly into X, is a base address. And if we go to well, it's 25A in terms of the offset from the beginning of the ROM. We can see here in the data, like, there's these values before zeros, 04, 0D, 0D, and then all of a sudden, EE3D, EE53, and these are like valid values, valid in terms of absolute addresses. It's as if in Mindstorm they would have encoded absolute addresses to read data from. And in particular, the kind of data we're talking about here would be, these are pointers, basically pointers to tables of vectors to draw. Like if I went to offset E3D within this file, can I like put a bookmark here? Yeah. What do I call this? Here. Like if I go to E3D, no, sorry, E3D, which is as an offset. No, not find. Go to $E3D. Here. That is the beginning of a table that ends with, I forget. I gotta go look at the code again. 001000FF. I forget which function, but basically it's a pointer to some table. There's another pointer, here's another one, and then that's it. But us, we're reading this here, 3408, which is not a valid pointer. And what's interesting about this code is that, like, it's saying load into xstat, and then it's saying I want to get this offset from here, which would be right now in the user stack +1, which gets us our C933 +1. So C934, read the value there, which is 4. And put that in A, and then we're expecting to shift it left by 1 to double it. That too is surprising, because wouldn't we want to just add 2? If we were trying to access this table, what I would be expecting for us to do is, if I just go back to it, here, let me just move this. Yeah, here. I would expect us to, like, get a value. I'm assuming what it's saying here is, get whatever value was stored here, and then we want to go to the next one. But that would not be a matter of shifting it left. If it was 0, we'd want to go from an offset of 0 to 2, an offset of 2 to 4. It just seems so strange. To shift it here. $48. Let me just make sure. Go to the CPU. Vectrex 48. Which is ASLA. Logical shift left accumulator. and that puts 8 into A, which ends up being this weird offset that X gets loaded with, and then that causes me to, in the function afterwards, to access it. Okay, so this ran and stopped. So I'm trying to remember my context here. Breakpoint hit at E9A1. What was the deal again with that? Oh, here. This is where, no, sorry, here. This is where U is pushed with C933. Okay, so not this specific time. It's C957. Here is C933. So this time it will push it, right? Info reg, U is C957, and then I'm going to step. Wait. Oh no, sorry, okay, so it just got pulled. It was C933, and then this pull here brought it back to C957, which just got pushed. Okay. Continue. Okay, so now we've hit the breakpoint again. Here it is C933 again. Yep. That's going to get pushed. So I just want to see. E9A1. Ah, I don't have enough lines in this damn buffer. Exception caught, and there we go. That's our bug. In the middle of draw VLPB. Just having this thought about setting up a run that I would trace to a file. Load this, set this, turn off the trace, and then break here Is that the right place to break? E59F. Okay, what I'll do is when I hit this address, I'll turn back the trace on and then continue. Let me try that. Just want to make sure that we run, yeah, the release, I have to build release. I am afraid of how huge this file is going to get, but I just need to give it a shot. I'm just refreshing here and I'm watching the size. So what I did is like if we look here at my input file, I start my debugger by loading symbols and setting that dude register like I always do, and I say turn off trace, set a breakpoint here. Oh no, wait, I didn't do this correctly. I want to turn off trace, set a breakpoint, continue. When I hit this breakpoint, turn back trace on, turn it on again, and then continue again. Yeah. Let's try that again. So run to output. Okay, so I hit my breakpoint and I'm now starting to trace. We can see it here, that the breakpoint was hit, then trace was enabled, and then it continued, and now we start getting instructions. But maybe I'm hitting that breakpoint too early, so. Wow. Interesting. I'll put some music on while we wait. It's interesting because it looks like the trace is growing a lot slower than before. Why would that be? I should also... Oh, this is why. Ah, okay. This is not working. And I know why. I think what happened is I hit my breakpoint again. I need to disable the breakpoint before I continue. Turn that off. Ah, so annoying. Whoops. That's it. So that's it because I hit the breakpoint again here. So I break here. Say set the breakpoint, continue. When I hit the breakpoint, I need to like disable 0, turn on trace, and then continue. Let's try that. I think I'm back in the same place. Oh, exception caught. Oh, this is good. Okay. It's because the problem is when I get an exception, it just keeps going and going and going. So let me just kill Vectrexy. No. And let's just delete all this. Okay. So now I have some 40,000 lines. That's good. So now I should be able to actually see what's going on here. C9 3D, C933. Interesting. Different trace. So I only have 1, 2, 3 of these instances. First one, I don't have enough context. And the difference between the one where C933 is pushed versus the one where, sorry, C933 is here. C933 is here as well. Didn't I see? Oh no, sorry, I was reading the wrong thing. So it is C933 in both cases. What am I gonna do? trying to think what is the next strategy for me. Like, what's the theory here? Is the theory that you should not have had C393, C933, I mean? Is that my theory? Like, is that where we're going wrong here? Or is it that, is it more the problem of 4 being written to C934 here? And the fact that that's read back, and the fact that that is shifted left. Like, what's the deal with this? Is that the problem? Yeah, there was something I had remarked earlier, was that it seemed weird that pull S was pulling the same value into U that it had before and after. Yeah, that was true. Let me try that. No, sorry, it's not here. Input. What? Okay. Oh, because I think yeah. Got a little pattern going now. Kill this. Hey, ABDCW. How you doing, man? I think I wrote exception. So I'm trying to figure out this bug. Tired. ABDCW says tired. How about you? You know what? I'm tired too. Tired of this damn bug. Fuck. Okay, here. Delete all this. So I added like these features to my debugger. I added watch points and all kinds of little features to help me debug this. And I'm getting closer, but still don't understand what's going on. I don't understand why this is happening. It's driving me a little crazy. So yeah, I wanted to take a look at when we pull from S in all of these different contexts. To have only a few of these. There's one here where we pull, and then do we know what U is after this? C933. Okay. So here, it was C933 before, and is C957 after. See, I find that interesting. And then here on the next one, U is C933, and Sorry, what's the next reference to U? And it's still C933. So that's interesting. And finally, because I think this is the last one. Yeah, this is the last one. So ABDCW. Is it almost midnight for you? Are you East Coast? C933 and C933. So that's like two cases where this is the case, where it was that before and that after. But here, yeah, that's one case, and then I have another one here where it's not that. So let's see. Pull and push. This is very different. Try to line this up. Yeah, so because this is an instruction that pulls PC, it actually changes the next instruction. That's why here it's EC14, while here it's EC17. Which is really interesting, actually. Because above it, they're pretty much identical. Well, yeah, the values in memory are not, but yeah, the instructions are. So why, how did PC here, man, I wonder if that's part of it. Because it's when I come here that this load 4 happens, that like messes everything up for me. And it's just like starting to wonder what the hell's going on. So we're pulling PC on both ends here, which had EA29. Then the next pull PC had slightly different. Like this guy's only 3 bytes off from this guy. But this one does a jump, whereas this guy starts executing this code. Trying to think where. So things that push the PC onto the stack are like jumps to subroutines, so JSR. Trying to look for JSRs in here. It's gonna be tough. Well, there's this one. Yeah, so like this one here, JSR EA91, this would have put EC17 onto the stack. Yeah, I mean, it wouldn't put its current address. It'll put the address of the next one to execute. So how can we come back to here? See, jump subroutine is 1, 2, 3 bytes, right? 1 for the instruction and 2 for the address to jump to. So that means that PC would be at EC17, which means that if we were to look on the stack and read it, we would get EC17, which is what, like, the kind of thing we see here. Just trying to think, how could EC14 be on the stack here? I mean, unless it could be, okay, it could have happened before this. Maybe we jumped to EC14. No, I don't know. Does that make sense? Jump to here. Jump. You know, again, what would really help me out is a call stack. Being able to put breakpoints and take a look at the call stack. Because I could see then, when I reach this one here, what was the call stack? How did I get here? I'm just thinking about I'm really trying to understand how, like, what is the right thing here? So we have a jump here, another jump there. Like, is the fact, okay, so when we jump here, like I said, it would have written EC17 to the stack. So when we return, we should be at EC17. How do we find again? I like it like this. Yeah, so this code always has this like pattern of using pull SPC. Find all in current document. Oh wow. It's interesting, right? Like this is kind of like all jumps and returns. Jump, jump. This pull would bring us back to this one. Jump, jump. Pull, pull. Okay, and the one that I was interested in starts at I'm looking for this guy. Yeah, it's this guy. Jump, pull, jump, jump, pull, pull, jump, jump, RTS, RTS. Line 146. F607. So no, I don't think I did that right. Oops. Those go together. Jump to this guy and then jump to that one. Okay, so let's see if this makes sense. Line 101. When we return, we go to EA43. EA43. Yeah, that's 3 bytes after this one. So that's sensible. And then the next pull is at line 113. Brings us to EA26. Does that make sense? EA26, yeah. Then we have a jump and an RTS here. So line 131. F5, F5. Okay, why? We have a jump to subroutine at line 116 here. What? E826 is one jump, followed by this jump here, followed by this return here. And what I don't understand is, if we're jumping to F601, we would have put E7, B7 plus 3 bytes onto the stack, which RTS should have brought us to. But when we returned, we're here. What? This is super weird. Like, if we look at these addresses here, when I'm at E7, B7, this program counter is here, we're gonna do a jump. And the way jump subroutine works is it says, well, push the current program counter to the stack, right? So that means, since this is 3 bytes, it should be what, 7, 8, 9, A. So E7BA should have been pushed to the stack, right? And then we do some code, we're all happy, and then we do return from subroutine, which should pop what's at the program counter, which will pop from the stack, what was pushed, which should put us at E7BA. And yet, that's not what's happening. I must be reading this wrong. Let me look at my code. So, CPU, JSR, so there's op.jsr. Yeah. Read where I want to jump to, push to the stack, the current program counter, and then set the program counter to where I want to jump to. And then RTS is pop the 2 bytes from the stack pointer and put that into PC. So what am I missing here? Unless something is messing up the stack, that's possible. Or this? Yeah. We're pushing a value onto the stack. Wow. We're pushing, what did I write here? Push SX. So whatever value was an X, we're pushing it. Oh. Ah, okay. Forgot about branch subroutine. Yeah, forgot about this guy. So branch subroutine. What's the difference again? Branch subroutine. Okay, so the difference between jump to subroutine and branch is what? Branch, okay, because branch allows negative or positive offsets, 1 byte or 2 bytes. If it's a long branch, it's 2 bytes. Whereas a jump to subroutine, you give it an absolute address to jump to. So that's the difference. What this means though is I'm supposed to be taking that into account when I'm doing my search. Okay, so let's do that again then, because what I have is not valid. I'll add BSR in here as well. Okay. Oops. What did I just do? EA3C, which is the pull. Just thinking here. Yeah, right. What I'm trying to understand is this EC17 versus EC14 that I was getting before. And trying to make that match up in my head. Like, how can that be? So these two JSRs, jump subroutine, jump. Then we have a pull subroutine with a PC, so these two go together. These two ostensibly go together. But before I do that, what is it I want to make sure of is EA91, EC14. Right. So I have EC14 here. I have another one here. And then I have an EC17. No, I don't. But EA3C. Actually, these are the ones I'm really interested in. Line 199. That doesn't chorus. Oh no. I think I searched in the wrong place. Oh no, I did search in the right place. Okay, so line 199. Sorry, go. Yeah, okay, so here it is. EA3C, EC17. So yeah, my question is why? Why? So let's see if I can eliminate some stuff here. So jump and pull. Jump, jump, pull. These two go away. These two go away. Branch, branch. This branch and this RTS should go together. Let me just double check that. 131. F5. Yeah, that makes sense. And branch is a 2-byte instruction, so F5, F5 is 2 bytes after F5, F3. This branch and this RTS. Jump, branch, pull. These two must go together. F607, yep. Branch and RTS. Branch and RTS. Okay, getting closer here. So there's jump subroutine with its respective pull ostensibly. Let's go double check that. 174 became E7BA. Yeah, that makes sense. right, so now what? This jump at line 114 should correspond with the pull at line 193. Which puts me at EA29. Yes, 3 bytes. And here we are at EA3C at line 199, and yeah, sure enough, EC17 here. That's what I would have expected. So these two are good. Yeah, so what this means is I don't have enough context for the other one, I think. Like I don't have the matching one for this RTS. So let's continue from down here. Jump in RTS, jump RTS. These two, these two, these two. Jump and pull. Let me just double check this while I'm at it. 567. E60, E60, 70, yep. Jump, branch RTS, branch RTS, branch RTS, branch RTS, jump and RTS. This is so boring. Make sure I didn't make any mistakes. 1262. F329, yep. I got it. Am I honing in here? It's gonna take forever. It's because the one I'm interested in is over here. Three, 5, 3, 4, 3. Oops. Why I'm at EC14 here. That's the one that interests me. Actually, you know what? EC14, so I guess it would be EC11 I should look for. Ah, there it is. This one here probably goes with the pull S at 35343. Yeah, look, I'm not even far. These two cancel. Yeah, and there we have it. So I'm not really getting much closer. I mean, what I mean is I'm not getting closer to understanding why we are getting this offset of 8 effectively. So, okay, I'm tempted to try something. So, like I said before, there is this possibility that in the end, this access in the cartridge space, as weird as it is, isn't actually incorrect. In the sense of Mindstorm was perhaps written in a way that there's a bug there, and it tries to access this address even though it shouldn't, and the Vectrex returns probably 0. I don't even know if that's true, but I don't know what it does if it tries to access a cartridge and it's not there. I assume it returns 0. It could be returning garbage too, I don't know. But let's say it returns 0. So then it would just be like, oh, it's a mistake in Mindstorm, and nobody ever noticed and nobody ever cared. So I'm like agonizing over this illegal access when in fact it's expected. That's a possibility. And if that's true, what I could try as a test is I could just say, allow all accesses to the cartridge to just go through quietly. You know, like here when I'm reading, just return 0. Or rather, in case, no, yeah, let's just return 0. And let's just see how far we get with that. Like what I want to know is, am I going to get another illegal access somewhere else, or do I finally get to an unhandled CPU instruction? That's really what I want to know. Oh, what's the problem? Oh. Okay. Let me bring this guy here. Turn off trace and just run this. Oh, no, and set my usual dude register, and now we run. See, that's interesting. It's interesting because when I wasn't returning 0, I was getting a crash really quickly. Hey, Fake Pyri. Fake Pyri is asking, or Pyri, Fake Pyri, I don't know. You tell me if I'm pronouncing it right. How does the Vectrex compare in complexity to the NES? So that's a good question. I think overall, in terms of emulation, like, okay, so the hardware is simpler in some ways. The CPU, well, actually, the CPU is more complex than the NES one. What is simpler is that I haven't seen any information about having like to deal with ROM mappers. I don't think any of the cartridges that came with the Vectrex had special circuitry to switch ROM banks. So that's one simplification. The other one is in terms of rendering, it's simpler because it's rendering just, there's no color, it's just black and white, and like it's a vector-based raster, right? So that's simpler because, well, I mean, yeah, it's simpler because I don't have to worry about like, you know, tiling, sprites, layers and priorities between the sprites and the tiled layers. Like there's none of that to deal with. It's really just, there's a vector beam, and in the Vectrex, it controls the vector beam. You tell it, I want you to move here, I want you to move there. So that's simpler. On the other hand, there are like so many NES emulators that have been made, and when I wrote mine, there was just a wealth of information. There's this like the NES dev wiki. If you go there, there's just tons of info, like lots of docs, they explicitly tell you how the rendering algorithm works with pseudocode that you can just kind of plop into your code and use that way. Whereas for the Vectrex, the story is quite the opposite. There are maybe 3 emulators that have been written. Information is scarce. So there's that, right? So it's a different kind of challenge. And yeah, the CPU is a bit more complex. So another thing that's cool for the NES is there's this like test cart that was written to test your CPU implementation. This guy Blarg, I think his name is, wrote a really cool NES ROM that like tries to exercise, like you need to make sure you have, I think, 6 instructions implemented correctly, and then it goes and using those 6 instructions like calls every other instruction and writes patterns to a certain area in memory, and then checks those patterns afterwards. And like you can use this cart to see if your CPU implementation is valid or not. That's really, really useful and awesome. For the Vectrex, I have no such thing, and the best I can hope for in terms of like comparing or knowing if my CPU is valid is to compare it against these few Vectrex emulators that exist. Generally speaking, I try not to look at other emulator code until mine is done. So I'm hoping to get as far as possible without having to do that. And if I do need to go there, I'll probably just, kind of take their CPU implementation and run it within my emulator and compare and stuff. So I don't know if I answered your question in terms of how does the Vectrex compare in complexity to the NES, but that's the way I see it. So this is pretty awesome. It looks like, if I'm not mistaken, let me see here. If I turn on trace, like we might just be in, either we're in some infinite loop, that's possible. Like we might actually be in the game loop and it's just running. Because I mean, I can see like, every once in a while here we have E. Here, let me actually load symbols so I can tell what's going on a bit more. Where is that again? Here. So Fake Pyre asks, do you have to emulate the CRT behavior? So it's actually really cool. The Vectrex, they just took a regular screen, like a regular CRT. They turned it 90 degrees so that it's taller rather than wide. So it's like 3:4. And they, from what I understand, they basically like just removed, like how in a regular CRT, it takes the raster and it moves, from top to bottom, left to right, doing the horizontal trace, then a retrace, and a horizontal trace all the way down. Then there's a vertical retrace. They like removed the motors that drive the CRT to do this kind of rendering, this kind of raster, row-based raster, and instead replaced it with some kind of integrator that you control through a chip. So you write code that tells, there's these BIOS functions that do it, but effectively what they're doing is they're setting a Y and an X value into registers, into this chip called a VIA. And what it does is it uses that to move the raster in arbitrary directions, which is how vector displays work. So that's what I need to emulate. I need to emulate the vector display of the CRT. And I'm not sure yet how I'm going to do that. So I've been focused right now just on the CPU. But I may actually now be at a point where if it is really running the game loop, it would be the time to start implementing the display. So I just wanted to see what this looks like. I can get like an idea if I'm in some weird loop or in some game loop by just looking at the code a bit here. See, like here, here the game, which is at EBB9 here. Anytime you see E, that's the game. If you see F, that's the BIOS routines. So here we're jumping into a BIOS routine called obj hit. Obj hit, obj hit. So lots of object hits here. In fact, see, it's not just that, right? We have some calls here to that are touching the vec string pointer. So this is usually when they want to display stuff on screen. Print string. Fake Pyri asks, how much RAM does it have? Actually, it has a tiny amount of RAM. Yeah, I'll show you. It's a map. It has 1 kilobyte. And of that 1 kilobyte, only 874 bytes can be used by the programmer. And part of that includes the system stack. Meaning that like the more you push to the system stack, or like the more subroutines you jump into, the more it eats into your 874. Usually you set your stack pointer at the end of this, and it basically moves in the negative direction. So you have to like consider that when you're programming the Vectrex. Yeah, it's very tiny. So the Vectrex actually is an interesting machine. Unfortunately, it's a machine that didn't work. Like didn't succeed on the market, and the main reason for that isn't because the machine wasn't good. It's because of the crash. The video game crash of 1983, 84. So the Vectrex came out in 82, and it did sell pretty well for a little while, but it was up against a bunch of competition at the time, and then the crash occurred, and then no one wanted to stock them or buy them, and so they ended up selling them for really cheap. I own one. My uncle bought it for me when I was it was like in 1986, so I was a kid. So yeah, he got one on discount, like they were just trying to get rid of them. But it's such a cool machine. But yeah, because it didn't sell well, it has a very limited number of games, and they were all basically made by, I think, by one guy who was working for the Vectrex company, which was called GCE. But yeah, it's a really cool machine. If you watch a couple of YouTube videos, and I mean, at some point I'll take mine out and I'll actually put a camera on it and we'll take a look and I'll show it on stream. Haven't figured out yet like what's the right way to do that, but like what's the best way to do that. So yeah, this is kind of interesting, right? Because like just looking at this trace here, it really feels like, yeah, look at here, VecJoy Mux 1X, VecJoy Mux 2X, Joy Digital. It's a bunch of like sound stuff, text again. So here's some BIOS routines that say move the raster, like move the vector display, the beam, I should say, move the beam to whatever's in D7F or whatever. Some intensity and brightness settings. I know recalibrate, they say you should call this, like this is a function that will get the vector beam reset back into to 0, 0, which is the center of the screen. And you're supposed to call this like once per frame, where frame is loosely defined there, but like, because if you don't, there's going to be drift. There's a recalibrate there, another one there. So yeah, like if I had to, just looking at this output, I would say we're in the middle of a game loop. And the fact that it's not crashing or anything means that even though I have not implemented every CPU instruction, the few that I have not implemented are at least not being called yet in the game. So Fake Pyri is asking, 0 zeros in the center, are positions then signed 8-bit or signed 16-bit? Yes. Now, which one it is, I think they're signed 8-bit from what I've seen. Like, if we look at the BIOS here, the routines from the BIOS, we can see like move, was it move 2 or something? Oh, I shouldn't do match case. That's why. What was it again? Let's look at beginning of line, move. Okay, so here's an example. Move draw VLC. This routine moves to the first location specified in the vector list, and like you feed relative x, relative y, relative x. It's always y first and then x because of the fact that the screen is rotated, I think, which kind of makes sense. So like if you turn your head, it's actually x, y. And I think it's 1 byte per. So yeah, so it would be like minus 128 to 128 in both directions. And I think that's what I read. I'm actually going to start reading like a lot on the VIA because it looks like I'm at that point now where I need to start implementing that. So the VIA is this chip that the CPU talks to that takes care of all the peripherals. So audio, input, and driving the vector display. So that's why you see here things like all these accesses to these registers. These are part of the 16 registers that the VIA exposes there, that these are memory mapped registers that the CPU writes to and reads from. Currently I haven't implemented it, so I just have this like dummy little class that all it does is have like a little array of 16 bytes for those 16 registers, and I just write whatever you ask me to, whatever the CPU says to write to it, I just write to it, and if it reads to it, and that's it. That got me this far. So what I wanted to do before I stop, because it is kind of super late here, getting to be on close to 1 o'clock, I just wanted to get a feel for how many CPU instructions I didn't implement yet. So what was my trick to do that? What I was going to do is, what I'm going to do is I'm going to count the number of entries here on this, because this is my opcode table, so this contains an entry for every single instruction. So I'm just going to count how many of these there are in here. Control Shift F, current document, find all. Okay, so there are 303 in here, and if I go to my CPU, go to my like big switch case of all instructions, I'm going to search for case 0x. And I'm at 255. So yeah, 255 out of 303, and it's 0, right? If you're a programmer. So 255. So about 84% of the instructions have been implemented. So that gets me right now looking like I'm running the game loop for for Mindstorm. Either it's the game loop. Actually, it could be that what we're looking at here is not the game loop, but rather the title screen of Mindstorm. I don't remember if Mindstorm like auto starts if you don't press anything. It may just remain on the title screen. See, this is when I need to take out my Vectrex and try it. But that's a possibility. It's just staying there. And I don't know if there's like an attract mode or something like that. Yeah, tough to say. I'd have to take it out and try. And it might make sense because of all the text writing and stuff that we saw in the output. It's possible. Maybe. So yeah, I think that's it. I think I'm gonna call it a night. I didn't really get much done tonight. I was hoping to figure out this bug, but I'm starting to really think it's what I said. It's not a bug in my emulator as much as it is just a bug in Mindstorm, possibly. So if it is a bug, I mean, I'll figure it out later. But for now, yeah, for now I'm satisfied with keeping it this way. So I do want to just commit this one change I made here, which is so I need to allocate at least 1 byte so that the BIOS can check that no cartridge is loaded. So this is a valid thing, even though now, yeah, so that's it. So I'll just do this. Cartridge, add 0 byte, add empty byte or 0 byte. How can I say this? Cartridge. Allow reading from byte 0 if no cartridge is loaded, so that BIOS can check for BIOS cart check. And I'll push that. Now what do I have left here? So I have this change I made in the debugger for executing instructions and catching exceptions. Yeah, I guess that's good for now. Let's get that guy in. Catch debugger. Handle CPU exceptions, or catch CPU exceptions, so that we can see the trace output. One. Do I need to put this detail? Buffered output gets flushed when exception is thrown. Okay, that's good. Yeah, this one I don't really want to check in because it's a hack. And this one, yeah, I need to do something about this. I think what I really need to do is a change that's like Like what I'm thinking is that if no cart is loaded, allocate the full space. And then assume that like Mindstorm is going to do the wrong thing, and that if we load a cartridge, then hopefully that cart is doing the right thing and only accessing memory within its address space. So that's potentially a viable thing. So instead of doing this allocate 1 byte, what I'd do is I'd allocate the full address space here. So yeah, this physical size. Physical size with a value of 0. Does that make sense? Oh, here, I'll switch to debug. So this should be like a 32K buffer for the no cart case. Yeah, 32K. So there we go. There's 32K in there. So this way, anything invalid will be considered valid. So I don't need to do this. And I don't need this hack. Let's run again with release. Set dude. Showing a little bit. Shouldn't crash just like before. And I expect that we get, maybe we only ever got that one read. Actually, that's really interesting. Let's see what happens here. So turn off trace, set dude, continue. Okay, so there's that access. That's 0. That's normal. That's a check if a cart's there. Now here's that access that has been plaguing me, 3409, that I think is a bug. 340A, 3408, 340B. Look at that. Look at that. Wow. It's crazy. See, now I'm like self-doubting, right? Like, could it really be that Mindstorm is making that many accesses into cartridge space? Seems really unlikely, right? Like if I just replace this with a trace point so that we just print, I'll put like cartridge read at address, comma X, I think. Let's try that. Cartridge read at, yeah, there we go. Look at that. Okay, so now like, look at that. This is it's going through a huge chunk of the cartridge memory and reading it. There's got to be a bug somewhere. This doesn't make any sense. Okay, well, I'll turn this off. And like after a while, if I turn it back on, I think I won't hit it anymore. Yeah, see, like we're done. So either there is a bug in Mindstorm where it proceeds to read a huge sequence of addresses like this in cartridge ROM space and then eventually stops and just moves on, or what I think is more likely, there's like a bug in my CPU implementation, and yet it's not buggy enough for it to crash or do something odd. So I don't know. But you know what? The next step is rendering. I'll start rendering, and you know, we'll see what it looks like on screen. We'll see how far we get, and then it'll be much more obvious if there's something going on with the CPU. So right now it's like shooting in the dark. All I can rely on is traces and, you know, what it looks like to me in the CPU. So yeah, this is kind of exciting because yeah, next step is rendering. Pretty cool. Having said that, I think I can commit this change. So I'll say here, cartridge, allocate buffer for the entire 32K of address space if no cart is loaded. This allows Mindstorm to keep running because it makes suspicious accesses to cartridge address space, which is either a bug in the game or a bug in my implementation. Push it. Yeah, and I said I was not gonna commit that. Okay, so that's it. Guys, thanks for watching. Those of you who stuck around long enough. Thinking about the next time I'll be streaming. Next week, actually, I'm going to be on vacation, so I'm not sure. I won't be able to stream on the usual times. So it might be a couple weeks before I'm back on stream. But in the meantime, I'll be reading about Vectrex rendering and trying to plan out how I'm going to tackle that. So maybe it's not such a bad thing. So thanks for hanging out, and yeah, see you soon.